Can you hear me out in space?
All right.
Brilliant. Okay, well, it's a great pleasure to introduce the fifth and final speaker of the afternoon, who is Nima Arkani-Hamed, who's going to tell us about quite a lot of things. So take it away.
All right. Well, I'm really delighted to be able to join you guys, even if only virtually. I'm talking about a line of work that my friends and I have been pursuing with a number of wonderful physicists and mathematicians over the past 12 years or so. But more specifically, the most recent things are over the course of the pandemic, work with Hadley Frost, Pierre-Yves Plamondon, Giulio Salvatore, and Hugh Thomas. And what we're talking about are scattering amplitudes. These are the most basic observable in fundamental physics. We care about them in experiments. They happen in the world around us all the time, the scattering of elementary particles. And in a very precise sense, they're really directly controlled by the deep principles of space-time and quantum mechanics. And indeed, thinking about scattering amplitudes played a big role in the development of the theoretical framework of quantum field theory in the middle of the 20th century. But we're really going to ask sort of an inverse question. We're going to ask, what is a new kind of question to which the amplitude is the answer? Now, the conventional question to which the amplitude is the answer is you throw particles in from infinity, they go back out to infinity, and you imagine, following Feynman and friends, that what happened inside was that particles came in, they hit each other, they banged into each other in all sorts of ways, and they went out again. So this is a picture of local evolution in space-time and unitary evolution in Hilbert space. So the conventional picture of scattering amplitudes, its purpose in life is to make the principles of space-time and quantum mechanics as manifest as possible. And I could speak for hours and have in other places about why we need to go beyond this to something deeper. But here, let me just say that we're really going to be asking for something else. We want to find these amplitudes, these fascinating, interesting functions, as the answer to a different kind of mathematical question that does not invoke the interior of space-time or the evolution of a wave function in Hilbert space, and somehow gets the answer as a consequence of some other kinds of mathematical and physical ideas. Amongst other things, this will allow us to see how this something else can give rise to the properties of amplitudes that we ordinarily ascribe to the presence of space-time and quantum mechanics. One of the key ideas in this subject is this notion of on-shell versus off-shell. Or real versus virtual particles. The conventional way of thinking about a real particle moving along is to specify its energy and momentum. But Einstein tells you that the energy squared minus the momentum squared, or the form momentum squared of the particle, is constrained to be given by the mass squared of the particle. So these variables lie on a hyperbola, the so-called mass shell. On the other hand, when we draw these pictures of Feynman, we have these lines in the interior of the picture that have momenta by conservation momentum, the Feynman rules that are just a sort of Fourier transform of the usual 1/r potentials that we're used to from high school are things that are quadratic in the momenta of these lines, things like 1/p squared minus m squared. And it's very important here that this p does not equal m squared. P squared is not equal to m squared. These momenta in these pictures are off shell and not on shell. The physical idea is to banish these notion of virtual particles. Amongst other things, their presence leads to horrendous complexity in the intermediate stages of the actual calculations of amplitudes, when the final answers are seen to be much simpler and exhibit lots of hidden symmetries and other magical properties that we're trying to expose from this other way of thinking about things. Fortunately, it's actually possible in many cases, and in particular ways of presenting the amplitudes, to understand what the fingerprint of space-time locality in quantum mechanical unitarity is on the actual function. So for instance, in the simplest way of, in the simplest sort of process, we would imagine what's really going on is four particles, we have a 4-particle amplitude, but maybe they're exchanging some intermediate particle of mass m. The amplitude for this process, when we just draw these simple tree diagrams, it has a pole, it has a resonance when the sum of the two momenta outside can actually produce physically this particle m inside, not as a virtual, but as a real particle. So the amplitude has a pole. When the virtual particle becomes real, that's the fingerprint of locality, that the amplitude of the pole in these prescribed places. And then quantum mechanics tells us something else. And in the neighborhood of that pole, the residue of the pole has a nice meaning that we have to be able to interpret it as actually producing the intermediate particle that then propagates a long distance. That's the pole, propagates a long distance before it decays out the other side. So the residue on this pole has to factorize into the product of two lower point on-shell amplitudes with no virtual particles. So it's possible to describe what locality and unitarity mean without ever having to talk about the virtual particles. Indeed, the rules of space-time and quantum mechanics are reflected in the amplitude in this in the way that I just said. Locality is that the only poles correspond to when a sum of the subset of the external momenta correspond to a physical internal particle, and unitarity tells us that the amplitude has to factorize on the poles. This is in the simplest case of tree amplitudes, but there's sort of avatars of this for more complicated processes that involve loops. So we have a concrete strategy then for finding this different question. We want to find a different question that's directly posed in the kinematical space that defines the scattering process without making any reference to a Hilbert space or space-time, but which nonetheless gives us the correct poles and the correct pattern of factorization. And over the past decade, there's a picture that's emerging that in the seemingly kind of arid and boring kinematic space, there is some little frisson of structure that begins as a combinatorial structure, then is associated with certain geometric ideas known as positive geometries. In turn, determine certain differential forms that have the properties, they have logarithmic singularities on these boundaries. And if we learn to integrate these forms at loop level, we'll get functions and make contact with symbols, and even over the past year or so, beginning to understand from this point of view, year or two, how we can even get non-perturbative understanding of amplitudes in some baby approximations. The words that go with these set of ideas are amplituhedra, which were the sort of first context in which at least my friends and I ran into these ideas, in many ways still by far the sort of richest and most interesting context in which they have arisen, but more recently isosahedra and even other kinds of observables that don't have to do with amplitude, but similar questions in cosmology. What I find exciting about these ideas is they really describe real world physics in a reasonable approximation, but expose hidden symmetries and new mathematical structure in a sort of pure magic, not in sort of esoteric questions about mathematical physics, but about real questions in the real world that they somehow expose pure magic and physics right under our noses. Now, I want to just give some invitation to how we can see this structure, already talking about the very simplest theory of scalars. So I'm going to talk about the simplest theory of interacting scalars. So there's no supersymmetry, anything like that here. And just imagine that we're drawing all tree diagrams, but the external particles are ordered. They're cyclically ordered, and I only draw planar diagrams. So these are the diagrams I draw at 4 points. These are the diagrams, some of the diagrams I draw at 6 points, and so on. Something to observe is that the only poles that show up in these pictures are sums of consecutive momenta. And we can actually visualize this more easily. The conservation of momentum tells me that the sum of all the momenta adds up to 0. So I can represent all the momenta end to end, and they form a closed polygon. And all the variables that we care about are the distance squared between chords in this, between 2 points in this polygon. So they're associated with chords in the polygon. Notice that the consecutive guys would just be P1 squared, P2 squared, P3 squared, and so on. These would just be the masses of the particles. I'll just set them to 0 from now on, which is, we can think of them as frozen variables, and not the dynamical variables. The dynamical variables, at least in this tree approximation, are just associated with the chords. And so in this picture, we can talk again about what locality and unitarity are. And it's very simple to see that that locality tells you that the kind of poles that the amplitude can have only correspond to non-crossing chords. So this would be an allowed pattern of poles that the amplitude could have, but this is not. There is no local picture in space-time that would give you something that would correspond to crossing chords. On the other hand, unitarity and factorization is the obvious thing that if one of these variables xij goes to 0, the amplitude literally factorizes into the product of the amplitude associated with two simpler polygons, where I literally cut along that chord ij. And a wonderful thing that one can discover that is not in all the sort of physics textbooks is that the pattern of poles has an interesting shape. Of course, this is the famous isosahedron. I've drawn the 4 and the 5 point examples. But for instance, if I talk about a 5-point scattering, the point is that there's a shape, in this case, a pentagon, where I can think of the edges as corresponding to all the partial triangulations just with one chord, and the vertices, the compatible triangulations, the complete triangulation in this case, with 2 chords. And we have an even more interesting picture at 6 points, which I've drawn here. Now, this is a fact. The fact that the pattern of the way the poles comes together is polytopal. This is not obvious from the standard sort of textbook formulation of field theory, but it's a true fact. And it's a true fact that also knows about factorization. And it knows about factorization because of this polytope has the wonderful property that the facet of the icosahedron are direct products of lower icosahedra in precisely such a way as to reflect the factorization of the amplitude. Now, back in 2017, with some friends, we ran into a very particular, construction of the icosahedron, which makes very close contact with the cluster polytope for type A. And the normal fan of this particular construction of the icosahedron is exactly the G-vector fan of the corresponding cluster algebra. Now, here I've only told you about the geometry, this polytopal geometry. That there's a longer story, but that the amplitude itself can be thought of as this canonical differential form that have logarithmic singularities on the facets and only on the facets of the polytope. The existence of the polytope actually manifests a hidden symmetry that this amplitude form has. To compute these canonical forms, one natural way is by triangulation, and one natural triangulation of the icosahedron actually directly produces Feynman diagrams. But this hides the projective invariance of the actual answer. There are other triangulations that are possible that are actually much more efficient than Feynman diagrams that manifest sort of term by term the projective invariance, and also other methods to get the form without triangulation. So the subject is not just a matter of sort of pretty words moving things around. There is sort of real content and really new expressions for the amplitudes that are simpler and exhibit hidden symmetries that we didn't know they had beforehand. And perhaps mathematically, something that is interesting is that the amplitude is a function, maybe more precisely a form, whose singularities capture the compatibility of combinatorics, or the G-vector fan, or the boundary structure of the positive part of the corresponding cluster algebraic structure. All right, so with that introduction, I want to just tell you about two things. First, about positivity, polytopes, and particles. So let's go back. So what we want to understand, just a picture for where this particular construction of the icosahedron comes from. Let's go back, and in this case, what is our kinematic space? Our kinematic space, the space that the amplitude depends on, is just the space of these xij variables, nothing else. So all we have is are these xij's. In this xij space, we have to ask an interesting question that somehow brings the icosahedron to life and then lets us connect the amplitude with it via this idea of the canonical form. Well, to begin with, we're just going to represent all of the x's on a grid, and since there's a natural cyclic structure to the problem, we just represent it on a grid in the obvious way as I've drawn here in the case of 7-point scattering. Every point in this picture corresponds to a chord of the polygon. And one interesting point is that there's a kind of to a physicist, there's a natural causal structure to this kinematic space, because if two chords cross in this picture, it corresponds, if two chords cross in the polygon, it corresponds in this picture to the 2 points, ij and kl, being the past and future corners of what we would call a causal diamond that fits inside this strip. And if we want to just keep one copy of all the variables, for example, we want to just keep 1, 3 and not 3, 1. They're actually exactly the same chord. Then we have to take a particular chunk out of this kinematic spacetime, and I'll choose this sort of right triangle chunk to illustrate in the rest of the story. So this is now our simpler problem. This is our kinematic space. These are the variables that we have, and now in this space we have to ask a question. And now this is the question that we're going to ask. We're going to demand that all these variables xij are positive, but for every one of these little meshes, we're going to impose a relation. Now, to a physicist, these are very natural relations to impose. They just look like a lattice version of the wave equation. If you imagine making these meshes finer and finer, this simply turns into the double derivative that would give us the wave equation in 1 + 1 dimensions. Okay, but that's it. So we're now going to ask, what are all the x's that are compatible with the x's, everything being positive, as well as satisfying these relations where the sort of source term of this wave equation are imagined fixed and also positive. And I'll just jump to what it looks like at 5 points. So if we just shoot out, if we look at this picture, you see that we get 3 equations for these 3 meshes, which we can use to solve for the 3 variables x24, x25, and x35 as a function of the rest. And if I demand that everybody's positive, I get in x13, x14 space this nice pentagon. And of course, you'll notice that if I look at this is a very particular pentagon, the location of all the facets is of course determined by these constants, CC prime and C double prime. But you see that the normal fan of this polytope is nothing other than the G vector fan of A2. And this is what the picture looks like for A3. This is exactly this ADHY realization of the associated. Now, in this extremely simple, familiar case, just for tree amplitudes, we can already make a connection between what looks physically transparent. This picture of the kinematic spacetime is exactly that of the Auslander-Ruyton quiver for type A, and the notion of time evolution in this kinematic spacetime is the action of tau in Auslander-Ruyton theory. Now, that was a story for the simplest amplitudes at tree level. When we go on to talk about more complicated amplitudes that have internal loops, this story connects Feynman diagrams to general surfaces. So what we're just talking about at tree level is associated with a disk, but via a standard connection between sort of ribbon graphs and surfaces, we can think of the general story, a general loop order, as associated with general surfaces. And so, just like with the disk, we associated this polytope whose facet structure reflected the cutting of the surface along chords. We can associate with any surface what we call a surfacehedron, which has a facet for every homotopy class of arcs. And beginning with the annulus, there are generally infinitely many of these arcs. This is related to the fact that the corresponding cluster algebra becomes infinite. And so this polytope is an interesting fractal structure, but the faces capture all the pinchings of the surface. So we can cut along chords, as we saw before. We can cut along chords with punctures to make a simpler surface. And we can also have closed loops on the surface that we pinch. And when we pinch them, we get the product of 2 lower punctured surfaces. Again, the normal fan of these polytopes, or these infinite polytopes, is the G vector fan of the corresponding cluster algebra, but with facets, with facets that include the interesting directions that are the limiting rays of the infinite cluster algebra that correspond to these closed surfaces delta. So the G vectors corresponding to these deltas are limiting rays of the other guys corresponding to ordinary arcs, and these polytopes have full dimensional facets for these guys as well. And in detail, the objects that we're talking about are slightly bigger than the cluster fan. For example, it's important for our story to also include closed loops like this, which are normally not allowed in the usual cluster algebra for surfaces, and all tagged and untagged variables are incompatible in this picture. That turns out to be more natural to make contact with the picture of with physics as well as the cutting picture of the surface. So I don't have time to explain how this works in detail, but I can at least show you some pictures of what these surfacehedra look like. So we already saw an example of the ordinary icosahedron, but here are just some sample examples for the surfacehedra for a once punctured disk with the 3 points, a 3 punctured sphere. These are the interesting cases, again, beginning with the annulus, where there are infinitely many arcs corresponding to variables that sort of wind around an arc that winds around the inner annulus many times, going from the outside to the inside. And so you see there's infinitely many guys, but they're asymptoting to this facet delta, which is associated with a closed loop going around. And even more interestingly, the case of Markov, or the once punctured torus, where you would expect that there are curves associated with every rational P over Q in lowest terms. And indeed, there's a sort of crazy 3-dimensional polytope that has the property that there is indeed a facet for every P over Q. And it manages to do it by having this interesting fractal structure. Here on the right, there's a sort of projection of this picture that at least impressionistically shows you, as you zoom in, how you see a facet for every rational P over Q. And just to show you in again what the point is, so For instance, this is the polytope that would correspond to a disk with 2 marked points and a puncture on the inside. It just turns out to be a hexagon. This is what it looks like for 3 points and a puncture. And the point is that every arc, we can sort of imagine cutting every arc. For instance, if I cut along this red arc, I add 2 more points and I should get just a disk with 5 points, or A2. So that should be a pentagon. And there indeed is a pentagonal facet. Or here, if I cut along this green arc, I should go back just to a disk with 2 points and a puncture, and that's indeed this hexagon, which is what we saw a moment ago. And similarly, exactly the same pictures for the 3 punctured sphere. Again, this case is a little more interesting. If I look at the annulus with the 2 marked points on the outside and 1 on the inside, and I cut on one of these blue arcs, then I should again open it up into a disk with 5 points, so a pentagon. And so it's hard to see, but there's infinitely many interlaced pentagons here. And all of these guys asymptote to this nice hexagon delta, which is exactly what I would get associated with pinching along that inner black loop, which again takes me back to this picture up here, the same hexagon. All right, now where do these come from? Once you make a choice of initial triangulation, then for any pair of arcs, we have a Skene relation of the form x plus y minus the sum of non-crossing, a particular set of non-crossing z's is equal to 0. That's the normal Skene relation. And in order to get these polytopes, the claim is that we just have to demand that these right-hand sides are just positive numbers. And it's very non-trivial that it's possible to choose a set of positive numbers so that all these relations are consistent and that everything remains finite. So that's that the C's have to scale in some very interesting way for this for the polytope to have the correct shape. Nonetheless, we conjecture and have checked in many examples that this is indeed possible, and that's one of the descriptions that we have for these polytopes. All right, so that's the story that connects particles, positivity. And so again, positivity here was absolutely crucial, that we demand that all these x's are positive, as well as that all these sort of the analog of these mesh constants that we saw before are also positive. So now I want to talk about something else, which is a sort of binary version of this positive geometry that then has the interpretation of generalizing from particles to strings. And what we just saw is that we can take the disk, for example, and we can associate these variables xij with the chords, and that there's a polytope whose linear inequalities capture the combinatorics of compatibility and of factorization. So the point of this polytope is that 2 chords that cross are sort of kept apart from each other by the polytope, and so the correct pattern of how the poles can come together is reflected in the facet structure of the polytope. But there's still some choice in how we draw the polytope. There's choice in these constants. So these parallel sides, for example, are always parallel, but where exactly they are can be moved around by changing these constants. The interesting thing is that there's an even more rigid structure that captures exactly the same pattern of compatibility. And these are the equations that Hugh talked about before. So since he talked about them, I'll go over at least this part a little bit more quickly. So with every chord ij, in the case of the disk, we associate this variable uij, and then we write down these interesting, very nonlinear equations that u plus the product, uij plus the product of all the chords kl that cross ij of the ukls is equal to 1. And what's interesting about these equations is that naively there's as many equations as unknowns, and so you would think it just gives just a variety. You think it just has the solutions in points, but remarkably, it's associated with a variety of the correct dimension. And once again, the word positivity makes an appearance. That if we demand that these u's are positive, then these equations also obviously force all the u's to be less than or equal to 1. But now the boundary structure is interesting, because if we saturate this inequality that a given u is positive by sending it to 0, all of the incompatible chords, all the ones that cross it, have to go to 1. because the product of all of them has got to equal 1. They're all less than 1, so that's only possible if they all go to 1. That's a sense in which this is a binary realization of the compatibility combinatorics, even more rigid than the polytopal realization of exactly the same picture of compatibilities. Now, let's say we talk about go back to the case of the disk, and we write down these equations. We have these five equations. You can try to solve them in many ways. For example, you can solve for all the u's in terms of 2 of them, like u13 and u14. More generally for the disk, you can check that they're solved by a particular set of cross ratios. So if we now imagine we draw this picture, and this is just a sort of a topological picture. There's no sort of metric in the disk here. But if you imagine this is really a Poincare disk, and there's a hyperbolic metric inside, then there's a very natural connection between the u's and just geodesic lengths in this picture. And that's associated with a very simple formula for the u's. So if you give me a bunch of ordered z's in the upper half plane, ordered z's on the real axis, then I can think about the u's as this particular cross ratio. And it's easy to see in general by a simple telescopic product argument of the sort that Q reviewed, that this furnishes a solution of the U equation. So this gives us a connection to hyperbolic geometry, and ultimately, as you'll see in a moment, to a more conventional picture of a string world sheet when we talk about amplitudes in string theory. But I would say this is just one representation of the solutions to these binary equations. There are other representations that, for instance, we can observe that the u's are naturally expressed as simple ratios of polynomials. And when these and in this way of writing it, we can also make manifest that when the y's are positive, the u's are positive. So this is a positive parameterization of the u's. This is very slightly nicer than this picture, where we sort of by hand have to say that the z's are ordered. Here we simply say that the variables are all positive, so it gives us a positive parameterization of u's. And this general way of writing the u's, again, for the case of the disk, you can write the u's as a ratio of polynomials of this form. This is the connection to the f polynomials, for instance, Q's talk. So that's the interesting thing, is that there's this binary realization of the combinatorics of compatibility in the case of the disk, and as we'll see for surfaces more generally. One comment is that there's a tight connection between this binary geometry and the polytopes that I told you about a moment ago. In fact, there's a sort of clue of the fact that there's a binary geometry there, and a clue to exactly these polynomials that show up in the definition of the u's in the structure of the binary geometry. And that has to do with the fact that if we go back to the pentagon, remember we got this pentagon by writing down these 3 equations that look like these little mesh relations for this picture. And a very natural thing to do, that's very familiar to a physicist when solving the wave equation with a source, it's very natural to take the idea of a Green's function, which is to imagine just turning on the source in one point and putting it to 0 everywhere else. And then once you have the answer to that problem, you just take linear combinations to get the general solution. The analog of doing that here is to imagine taking these sources, these mesh constants, C, C prime, and C double prime, and putting one of them, all but one of them, to a 0 and seeing what you get. And what you get is that this pentagon degenerates to very simple pieces. If you only turn on C, it degenerates to this interval. If you turn on a C double prime, to this interval. If you only turn on C prime, to this triangle. And you can further think of the entire polytope as a Minkowski sum of these simple pieces that are just weighted by these mesh constants. And these simple pieces actually know about those F polynomials. You can think of these simple pieces, the Minkowski summands, as the Newton polytopes of the corresponding F polynomials. So the fact that sort of tells you about the F polynomials and ultimately motivates the existence of the underlying binary structure is this non-trivial fact that the polytopes that are capturing the compatibility, sort of linearly capturing the compatibility. They're not random presentations of these associated. They're very particular presentations that realize them as Minkowski sums of simple pieces. And the simple pieces, in turn, are the Newton polytopes for the corresponding F polynomials, out of which you can build the U's that satisfy these binary relations. Now, the main reason that physically we're excited about these binary relations is that they give a very natural path to generalize from particle amplitudes to string amplitudes. And this is something that we see already at tree level. If we take the very simple form, which is just a d log form in all of these positive y variables, and we imagine just integrating it from 0 to infinity. So this d log form and these positive parameterization of the u's, you can think of as a canonical form on this binary geometry. It has logarithmic singularities on the boundaries of this binary geometry. But clearly, if I just integrate this from 0 to infinity, do nothing else, I'll just get something logarithmically divergent. So to get something finite, we're going to sort of borrow, take inspiration from the from Euler's presentation of the beta function, and for every chord at tree level, and exactly the same formula will be used for any surface. For any chord, we'll write down the product over x, ux to the power of some parameter alpha prime times x. If you remember, this x had units of momentum squared. These alpha prime has to have units of inverse momentum squared, or length squared. So we would physically call this a string length, and the particle limit is taken as this alpha prime goes to 0. Now, clearly, if alpha prime is very small, this is barely regulating this divergent integral. So we expect the answer to diverge like 1 over alpha prime to the power of the number of integration variables. And so we'll just put an alpha prime to the number of integration variables up front, just to take care of that fact. All right, so this is a naturally motivated integral, but the deep thing about it, the important thing about it, is that it preserves factorization. It preserves the sort of fact that as a given x goes to 0, the amplitude factors into the product of two smaller amplitudes, even at finite alpha prime. And that it does crucially thanks to this binary property. So the point is that if I imagine taking this amplitude as a function of all of these chords and non-zero alpha prime, and I take a given x to 0, what happens as I take that x to 0? Well, there's a divergence that goes like 1 over x, but that's localized to the neighborhood of where some uij goes to 0. But because when uij goes to 0, all of the UKLs that cross it go to 1, they drop out of this integral. 1 to a power is equal to 1, so they drop out of this integral. And what I get is just the exactly the same integral, but with the u's on the left and the u's on the right. And this holds even at finite alpha prime. Okay, so as alpha prime goes to 0, this is going to reflect the factorization for particle amplitudes that we knew that we wanted to have, but it continues to have this interesting property even at finite alpha prime. And this turns out to just be a way of rewriting the well-known Kobe-Nielsen formula for tree string amplitudes. But in this way, we see a sort of more structural connection between particles and strings. That we started with this very simple geometry that controlled the combinatorics of compatibility. The binary version of that geometry takes us from particle to string scatter. So if we look at the very simplest example of 4 points, here the U equations are especially trivial. Just U13 for this chord plus U24 is equal to 1. So here are the trivial positive parameterizations for the U's. And if we shove them into that general formula that I told you, we get the Euler beta function. But in this context, it would be recognized as what physicists might call the Veneziano amplitude in string theory. You can see that as alpha prime goes to 0, we get just 1 over x13 plus 1 over x24, which were the sort of particle amplitudes that I talked about before in this simplest case. But these gamma functions have infinitely many poles, and those poles are interpreted as excitations, of massive excitations associated with the string-like character of the amplitudes that we're talking about, not just particle, but string-like character. So that's the story at for the disk at tree level. But the claim is that there's a binary realization for all surfaces, where for every arc x, there's a formula of this type, where now the exponents are just the intersection number of the curves x and y on the surfaces. This is again very closely related to the Fock-Goncharov picture for the compactification of Teichmüller space. You can think of these U's as providing a global description of the compactification of this Teichmüller space, this binary description where U's are where the given boundary is associated with just some U going to 1, and that's crucial for being able to write down these string integrals and make connection to physics and amplitudes. There's a few concrete solutions of the U equations that are either associated with F polynomials or with hyperbolic geometry. Perhaps as we study it more, we'll find other ways of solving these U equations. But anyway, but a number exists. The solution a la F polynomials is what Hugh talked about, and also a la the connection to hyperbolic geometry I mentioned before. One thing I want to say is that I've stressed that the U's go to 0 on the boundaries of the space, and so that's the first thing that you might think of doing is just writing down these string integrals just with the U's corresponding to the curves on the surface that can go to 0 on the boundaries. Those are non-self-intersecting curves. And if you write down this string integral, and the only curves that you put in here are non-self-intersecting curves, you get a kind of stringy amplitude that has many properties of real string amplitudes. Back in the summer, we even wondered whether these might be real string amplitudes in disguise, but we now believe that's not the case, and these are some kind of baby version of string amplitudes. That's because we now understand that the most natural thing to do is to include all the chords on the surface, including self-intersecting curves. Now, if you have a self-intersecting curve in these U equations, that variable is going to occur in both terms because it intersects itself. So you have U plus the product of all the U's, but if it's self-intersecting, that variable will occur in both terms, and so we can't send it to 0. Nonetheless, it appears that if we add these self-intersecting curves, we get an even richer set of infinite products. And what we seem to get are real string amplitudes, not just sort of baby string amplitudes, but real string amplitudes. In the disk, we never saw these guys, so that's why at tree level, everything worked even with ordinary non-self-intersecting curves. But beginning at one loop, there's a difference between these two pictures, and including all the self-intersecting curves seems to give us real string amplitudes. These appear to be some new representation of string amplitudes. And what I find exciting about it is that we don't sort of have to begin from the top down from a declaration that we're starting with strings and taking alpha prime goes to the 0 limit to discover something about particles, but we can sort of work more bottom up by starting from the picture of the compatibility of poles for particles and see that it can be binarified in now a variety of ways to extend to strings. But just to give you one example of what of how we get the ingredients that are seen in a somewhat unfamiliar way. Yes.
Can you hear me? Do you mind if we bring things formally to a close?
Okay. Yeah.
At some, is this a good moment? I mean, there will be people who
I
are
really
to continue.
Yes. I have sort of one minute and I can close. Is that okay?
That's okay. Yes.
All right. Great. All right. So yeah. So this is just an example of the sort of very simplest the very simplest one loop problem where there's where if you include all these infinitely many self-intersecting loops, we get these very simple set of U variables, a simple set of F polynomials. But I don't have time to explain why we're forced to have this the exponents that scale like J squared, but that's sort of forced on us by the dictionary with physics. And this is an interesting representation. This infinite product ends up being just a Dedekind eta function, which is exactly what you expect in the real string amplitude in this case. And if you only included the non-self-intersecting loops, you would get this, as I said, this baby version of the string amplitude. And indeed, in general, for the annulus, these infinite products give us the correct Jacobi theta functions that we expect in real one-loop string amplitude. But this is a way of representing the string amplitude, which is really quite unfamiliar. Finally, I just want to say that all these notions of factorizing amplitudes for quote-unquote particles and quote-unquote strings can be associated with much more general quiver representations, a la Hughes talk. And it's a very interesting question what the physical meaning of these quote unquote amplitudes is. And it might even be related to the content of Nastya and James's talk. So let me just end by saying that over the past decade, we've been seeing concrete examples where the rules of locality and unitarity, space-time and quantum mechanics, are emerging from more elementary mathematical rubric. There's a common theme of the story of amplituhedra and surfacehedra and so on, are notions of positivity and topology in kinematic space. And these sort of very minimal things seem to be all that's needed to breathe sort of physics life into otherwise seemingly austere or empty territory. And a really fascinating thing is the ubiquity of cluster structure everywhere in this story. That seems something deep and important to understand better why this keeps happening. Thank you very much.
That's brilliant, thanks. Okay, sorry to stop. Are there any questions in the room? Can I ask one question myself?
Sure.
You said time evolution was tau.
Yes.
The direction of tau in this quiver. Why wasn't it tau inverse?
Oh, it could be tau inverse as well. So it's a question. For example, if we go back in this, you just have to choose one. If I go back to my picture here, so for instance, you know, the important point as far as this picture is concerned is just that if you give me the values of the x's on this sort of past part of this quote unquote space-time, then I can predict everything in its future. So everything in the future is solvable in terms of the quote unquote initial cluster in the past. But it's equally true if you give me everything in the future, then I can solve for everything in its past as well. So it doesn't make any difference whether you use tau or tau inverse.
But it does make a difference to physics which direction time goes in.
Yes, but that's right. But that's the equations of physics are also time reversal invariant, and the way the direction of time comes in is something very far removed from this story about the increase of entropy and so on and so forth. Yeah. Okay,
that's because in representation theory we know which direction tau goes in.
Ah.
So anyway, okay, thanks. Okay, thanks for that. Are there any questions in the chat? So we have put a link in the chat for anyone who would like to talk a little bit more. If Nima, can you hang around for a tiny bit longer?
Yes, sure, certainly.
Most people who want to go and drink some wine, I'm sorry we can't offer you online wine.
No, that's fine.
But if you look in the chat, so Peggy has set up an alternative Zoom link for people who want to continue, and the formal proceedings we have to bring to a close and let the institute go home. So this Zoom link, just to re-emphasize, this Zoom link is going to go down shortly, but there is a Zoom link in the chat, sort of Garretown style, for people who want to discuss a little bit more with Nima now. Okay, thanks very much, and thanks to all the speakers for this afternoon's session. We'll see you all again tomorrow at 1 o'clock again. So thank you.
Этот линк сейчас закроется. Вот.